In this video, I'd like to help you analyze from energy principles an interesting athletic accomplishment. I looked up on Wikipedia to find out that there's this race that happens each year up the steps inside the Empire State Building. And the world record holder is an athlete by the name of Paul Craik, who climbed 1,000 feet of steps inside the Empire State Building in a time of 9 minutes and 33 seconds. That seems pretty fast. What I'd like to do is take a look at this from an energy perspective using the work kinetic energy theorem, and also calculate what his power output is, like how powerful of an athlete is he. How does it look to me to begin with? Well, if I were to draw a little picture of this, I first see Paul at the bottom of the steps, and he's not moving. And then later, I see him at the top of the Empire State Building, huffing and puffing, but also not moving. So initially, he starts with no kinetic energy. On your marks, get set, go. And at the end, he also has no kinetic energy because he's stopped. So from the start to the finish, there's no change in kinetic energy. Now, from an energy perspective too, we can think about potential energy. Since he's down here at the bottom of the steps, he has no potential energy. And up here at the top of the steps, he does have some potential energy equal to an amount we could calculate if we wanted to, mgh. That's the potential energy due to gravity. But in order to calculate these energies, looks like we're going to need to know Paul's mass. So I don't know what to do about that since it's not given, except maybe we'll make something up. And I think an estimate of 80 kilograms is reasonable for a male athlete. That's like 180 pounds. So let's just put some numbers to this. In the beginning, no potential energy and no kinetic energy. At the end, no kinetic energy but some potential energy. Let's figure out how much that is. You need to multiply mgh, the mass, 80 kilograms. Might as well just use g as 10. So I have 80 kilograms. Might as well just use g as 10 meters per second squared. And the height is 320 meters. And if you multiply those out, you get, looks like 256,000 joules. Or if you wanted to say that in scientific notation, round it off a little bit, it'd be 2.6 times 10 to the 5th joules. 1, 2, 3, 4, 5, and then I rounded the 5 to a 6. All right, well, what does the work kinetic energy theorem have to say about this? It would say that the total work done on Paul is equal to Paul's change in kinetic energy. In this case, that happens to be 0. So at first blush, you might think, well, there's no work involved here because there's no change in kinetic energy. But in fact, the total work is made up of all the individual things that do work on Paul. So what are those? Well, I surely see that Paul did some work on himself by converting sugar and fat metabolically into useful mechanical energy. But he also did some work against gravity, the only other force he's really fighting here, because this is more or less frictionless. So these two energy exchanges have to balance out to 0. So whatever energy added to Paul metabolically was taken away from gravity because he went up but gravity pulled down. So the work done by gravity would have to be negative. So we would like to figure out what is the work that Paul did on himself in order to put this accomplishment into some perspective from an energy point of view. Now in physics, we have no way of calculating energies produced metabolically. That's for a different class you might take down the road. However, we do have a way of calculating the work that Paul did against gravity. Because the work that Paul did against gravity is accumulated in potential energy. So, we can really see here that the work done by gravity is equal to minus 2.6 times 10 to the 5th joules. First of all, I used potential energy to calculate the work done by gravity, and additionally, I forced it to be negative because I understand that Paul goes up, but the force pulls down. But that must mean that the work that Paul did on himself was equal to plus 2.6 times 10 to the 5th joules. The reason it has to be plus is because Paul has to add whatever gravity takes away. So that's 250,000 joules. Is that a lot of energy? I don't really know. You could look up online if you wanted to a conversion factor that converts joules into food calories, kilocalories. But for now, we're going to skip that and try to calculate his power output. His power output is the work that he did divided by the time it took him to do that work. Power is measured in watts, which is joules per second. So we have his the work that he did here, 2.6 times 10 to the 5th, and we have the time it took. Going to definitely need that in seconds. So I'm going to need 9 minutes and 33 seconds in seconds, so 9 minutes times 60 plus 33. What do you get for that? I get 573 seconds. Do you agree? So you take his energy output and divide it by his time. What do you get when you do that? I'll let you do the heavy lifting here, but I get around 450 watts. Joules per second. So 450 watts, what sort of comparisons do we have for that? Well, really not too many. There is another unit of power which might give us a better comparison, and that is the horsepower. The British unit of horsepower is equal to 746 watts. So what's Paul's power output in horsepower? Well, if you divided 450 by 746, you'd end up with his power output in horsepower, and I get around 0.6 horsepower. And that's a fairly substantial power output. I do happen to know that some of the most powerful athletes are in fact cyclists and rowers, as it turns out. And that for short periods of time, the best human athletes can do is a power output of approximately 1 horsepower, maybe a little bit more. So this is really a pretty spectacular accomplishment to expend energy at the rate of 0.6 horsepower for a total time of about 10 minutes to climb to the top of the Empire State Building.